Welcome. So let's get started. If you were, so if you were online yesterday and all of a sudden, so stuff stopped, there was, a power outage. So sorry about that. Or so someone turned off the lights in the middle of class because they didn't like what I was saying. Please refrain from doing that till after class this time, if so that was the case. We are going to be talking today about clustering. It's kind of a new type of methodology of data analysis, and so we're going to start this section today. Again, I won't get into any of the algorithms today. I'll mostly try and define what it is, and there's kind of some more some different kind of things to understand before we can jump into the algorithms, which will be in the following lectures next week. So if we look at the schedule, we have finished the section on dimensionality reduction. Again, if you missed the second half of the lecture on Tuesday, I've recorded it. There are 2 YouTube links now, so part 1 and part 2. We'll talk about this today. We'll talk about clustering in general. So assignment-based clustering, which is kind of one class of clustering approaches, probably the most common one. And we will basically focus on this type of clustering in this course. There are plenty of other types of clustering. The book covers some of them, but there's kind of just lots and lots of variants. And I'll kind of explain why that's the case. We will basically define what this is and kind of the core, probably the most challenging structural part about thinking about how the assignment is done by talking about Voronoi diagrams. And then on Tuesday next week, we'll talk about kind of 2 of the most popular algorithms. So the kind of the k-means formulation and Lloyd's algorithm, talk about on Tuesday. That's probably the single most popular thing. When people think about clustering, they usually think about that. And we'll extend this to mixture of Gaussians and maybe some other variants on. So Thursday, mixture of Gaussians seems like it's much more complicated, but once you understand Lloyd's algorithm for k-means and things like dimensionality reduction and everything else, and SVD, it should be actually, it's a pretty straightforward extension. Okay, so it's just 3 lectures on this. Okay, notice quiz 5 is also today. So I will stop the lecture a bit early, so you have half an hour to have take the quiz in class again. So what I recommend, because I can be here to answer any questions you have, and then but it'll be open until midnight. So you'll have or until the end of the day, 11:59 or something. So you have a chance to take it later as well. Again, don't forget the cheat sheet. You can turn in as well. So have that ready. The last quiz 6, will be not in 2 weeks, but in 3 weeks from today. Partially that's because it would fall on Thanksgiving, but when we don't have class, but also because it's the last one and it's going to cover kind of clustering and the first part of classification. Okay. And then homework 4 is due on Tuesday. Don't wait till I know it's starting to become a pretty busy time of the semester, but don't wait till the end of kind of the last minute to do it. This one, has stuff that traditionally has been challenging for students. So there's an extra TA office hour. So today I'm available after class and on Friday, and then early next week there's a bunch of office hours. But look on Canvas. Otherwise, I'm usually pretty quick to respond on Canvas, so that's another good place to ask questions. So okay, any question about the schedule, where we are? Great, so let's get into the lecture. Let's see what we can cover before we run out of time and have to take the quiz. So clustering, yeah, so clustering, we talked about kind of two, just the mean as the initial thing we talked about very early in the semester, and we'll come back to thinking about the mean as representation. But otherwise, two other sort of analysis techniques. We talked about regression and we talked about dimensionality reduction. So, so clustering is a kind of a different form, like those two. And let me kind of define. The input here is again going to be a set X, and we'll say that this is a subset of RD. There are no labels again, so this is going to be an unsupervised problem. We're not going to be able to use cross-validation. It's going to be like dimensionality reduction. And what we're going to want to find is some sort of simpler shape of the data. But the shape is going to be different from the dimensional reduction, where we had a high dimensional data and we want to reduce it to a lower dimensional so subspace. Here we're going to reduce it to kind of a set of regions or points. Okay, so we'll think of X again being a set of these points, right? So it could be a set point. You typically end up drawing pictures like this when you're talking about clustering. The other part of the input, which is often so sort of implicit, is some sort of distance d, which is a bivariate function from RD cross RD. All right, and so it just takes in the data and some distance. In this class, we will entirely talk about the distance between xi, xj as just the Euclidean distance, right? So this is Euclidean, and that is if I have xi, xj as two points, it's just going to be the straight line distance in between here, the length of this line, okay? That's what this distance is representing. In fact, clustering as a formulation is more general, and it doesn't need to be, I think of these as points in our d-dimensional vectors, which we're hopefully used to working with at this point. But this could be more general. All I need is a set of data and a distance I can define between those data, where points that are less similar to each other have a larger value. Things that are more similar have a smaller value of the distance. The sort of methods we are going to be talking about in this class, though, require that the data is in RD and that the distance is going to be Euclidean. Okay, so within this class, we're going to again talk about the simplest, kind of most common form of these, and that is going to assume these properties. Okay, but if you look in the book, you can see other variants of distance of clustering, and some of them do not rely on these these assumptions, right? So it could be that you have kind of a bunch of people on, so Facebook, right? And they have attributes to them, right? Some of those are defined by the graph. Other things are defined by what images they've uploaded, so some sort of properties. And as long as I can define some distance, which I think says how similar things are, I can think about clustering these objects. But we're going to think I've somehow converted people into data points, which is kind of common. And then I'm using the Euclidean distance. Okay. Okay, and so these are kind of like an example of one of these data points. For instance, xi, this could be one of the data points. And then the clustering, the goal of clustering, the goal is to group the, so data points x into generally, let's say S1, S2, up to Sk. These are going to be all subsets of X. They're often going to be disjoint subsets. For the k-means clustering we'll talk about, they will be disjoint. For the mixture of Gaussians, they will not be disjoint. Okay, but into these subsets, so if I have xi prime in Si, then xi, then this, let's just say the distance between xi prime is small, and if I have xi in Si and xj, right, j in xj, then dxi xj is going to be large. Okay, so if I drew a picture here, think of this as being the set S1, this is S2, this is S3, and I look at this distance between 2 points in the same cluster. I want this distance to be generally small, and if I look at a distance between 2 points in different clusters, I want this to be large. Okay, that's kind of the idea. Finding the groupings of points. Yeah.
So how do we define how many clusters?
Yeah, that's so that's a great question. Kind of similar question when we're doing dimensional reduction. How many dimensions do we reduce it to, right? You kind of want, I mean, the answer I'll give you now is you kind of want to choose a k that's as small as possible so you can achieve this, that inter-cluster points are close and far cluster points are large. What does that mean? I haven't even told you what should be large and small and what other things should I say about the clusters. This is kind of a, yeah, so this is an interesting problem. For most of what we'll talk about in class, k will be given as the input. And so you'll just be told, okay, you want to find 3 clusters in this case, right? And I'll tell you that, right? But this is a really important question. How do I determine how many clusters there should be? There are some methods how to do this. And I think we'll talk about a few of these issues. There's kind of a way to noticing, like as you get more and more clusters, the points within a cluster, you know, this first condition, that the points inside of the same cluster are going to be small, that you do better and better on that, right? Because there are fewer and fewer points, so the points that are left over are going to be closer together. But the other one, you kind of start to do worse. I might, if I split one of these clusters into 2 clusters, right, then some of the points are going to be, that are in different clusters are then going to end up being close to each other. So I don't achieve the second one, that the different cluster points are going to be large from each other. And it's, you can kind of see kind of some trade-off, and maybe you can find a good balance, but there's not one way of answering this question, what is the right way to do it. I'll try and give you some intuition on how to answer that, but yeah, this is a great point, and to that the notion of clustering is much vaguer than regression or dimensional reduction, and that what is the actual goal here. The goal is often quite vague, and you often see pictures like this drawn in the plane, and it shows, okay, there are 3 clusters, right? My actual advice is if you have data in 2 dimensions, I would plot it and take out a marker and try and draw circles around it. And that's probably the best way to actually identify clusters. Decide if you think there are subsets, and if there are, then draw circles around them with your pen. You can run algorithms that'll try and automate this, but they all have kind of some potential issues with them. And one's not necessarily going to be better than the other. And plotting it will really give you a lot of insight into what's going on. We will do an example next week. I think I moved to next week where we'll plot stuff and you'll see some nice examples. But data is not often this nice. In 2D, it's either easy or it's hard. In high dimensions is when you want to use the automated techniques, because I can't draw a picture. What often happens so dimensions, and even in low dimensions too, is that you'll get data, like the most common data I see is often, there's some like maybe the origin, you're more likely to have points, and you're going to get a lot of points, and they're going to kind of dissipate kind of as you go out. This is what I often call like a smear or schmear, something of points. And okay, when I get points that kind of look like this, how do I do clustering on it? So what should I do? Basically, I should not run clustering if the data looks like this. You plot it and the data looks like this, and this is the distance you want to use. It's the straight line distance. There aren't different clusters in this data. Okay, maybe there's one cluster. Says, okay, all the data points are in S1 and nothing else is in S1. That was not very helpful. It's not very illuminating, but this is not an uncommon way that data actually looks. There aren't these nice subgroups of points in you see in 2 dimensions, and this may be like a higher dimensional phenomena. So it's even harder to even necessarily know that it looks kind of like this. So I'll try and give you some guidance on this, but I feel like we need to talk about clustering in this class. It's a very common thing. Sometimes it is extremely useful, but you should not assume there are always going to be clusters in the data set. There are not always nice clusters in data. Okay, don't assume there are. Things like regression, I can always find the best model, and I can using cross-validation, I can evaluate how well it's working, and I can get an honest picture. Okay, this is the model, and on the held out data, this is the expected error I get based on this model, and you get a good sense of that. So dimensional reduction in high dimensional data, even if you just put random data in high dimensions, there's often lower dimensional subspaces that capture most of the variation, even if there's not actually structure in there. Dimensional reduction just tends to work. There are results that say that if you're an arbitrarily high dimension, the actual ambient dimension that can capture almost all the distances is defined based on like roughly the logarithm of the number of points, right? So kind of dimensional reduction by default almost always works, at least to some extent. Clustering, that's not the case, okay? It's heavily studied because it's kind of so vague in what the definition is. So there are lots of variations on it. And we'll see there's some interesting kind of mathematical challenges. We'll talk a little bit about issues with the Voronoi diagram today, which is kind of something that's complicated and it's been studied because it's complicated. Okay. So just, I want to give you that perspective that clustering is not, you should not always assume there are clusters in data. Okay. However, it's a very popular thing. We're gonna talk about it. We're gonna talk about the most popular variants of it. And there are cases where it's useful to kind of identify these sort of groups within the data set. If they do exist like this, it'd be great to know about that. And we'll talk about how to automate kind of finding those groups. Okay. Oh, all right, so the type of clustering we're going to talk about, the variants of clustering are going to be assignment based. So clustering, okay, and this has a particular form, and so I think a quite intuitive form, and it fits in with the other themes of the class, is that each cluster S, I in this set S1, S2 up to SK is so associated with a point. I think I'll call this point C of I, and this will be a point in RD in this class. I think the book might use lowercase s, but it's hard to tell at least with my writing, sometimes upper and lowercase s's look too similar. So we use a lowercase c. And this we'll think of as like the center of the cluster. Okay. Okay, so again, if we look at some nice data, ideal data of what we think this should look like, right? And there's going to be these 3 clusters here, S1, S2, S3. These are the subsets of points. There's also going to be these centers, C1, C2, and C3. These single points, which are going to be kind of the representatives, okay? The representatives of these clusters. And what's nice about thinking about it in this way is that I can then think of from a data point to the center. So let's say this is X1, right, or Xi, right? Then this blue line here is the residual of Ri, right? This residual is going to be the distance from Xi to its assigned center, C. I'll say C1 in this case, right? Where this case is, right? So this center is this particular center in this case, right? And these are linked somehow. Okay, so it's mapped to its assigned center. Every point is assigned to one of the centers, and that tells you which cluster it is. They have the same index, right? So if there are 3 clusters, there are 3 centers and 3 subsets, and depending on which one it's assigned to. Okay, and in order to define this, we kind of do something like a projection, right? We're going to do something. It's kind of like when we projected every data point onto the low-dimensional subspace. We're doing that now, except we're projecting onto a set of these points. Okay, so I'm going to say that I'm going to define a function here, and this is going to be phi of C. I'll say that C is going to be the set of the centers, C1, C2, C up to CK. Okay, CK of which is going to be a function from RD to the set of the centers, and it maps it to the closest point, right? So phi of C of some point X is going to be the arg min Ci in the set of the centers of the distance from X to Ci. That's not X1. Okay. From X to Ci. So I'm going to map everything to the closest center. This is like a projection we did to a subspace, but it's a bit trickier because I can't define this with like a dot product anymore. Okay, with the projection, I could define this through these dot products. It's this nice linear function, a lot of nice properties, and we exploited those properties heavily when talking about dimensional reduction. That's why the SVD worked, to find within PCA to find the best subspace, because it was this nice linear function. We don't have that anymore. Instead, I'm mapping every point onto the closest center, right? And that, I mean, hopefully that makes a lot of sense. Every point is mapped onto the closest center. That's what this phi map is doing, right? It's mapping every point onto the closest of the centers. And now my cost function, at least the cost function we will talk about in this course, is going to be the sum over xi in x, or let's call this xj in, yeah, let's do xi in x of the Euclidean distance from xi to the closest center of xi squared. Okay, so again, sum of squared errors. Right? I want to minimize the sum of the squared errors, sum of the squared residuals, but now the residuals are defined by mapping onto the closest of the centers instead of onto a subspace, or instead of in the response variable y that I have in regression. Okay, so I'm minimizing the sum of the squared distances onto the set of centers where I use this phi map, which maps to the closest center. Right, this again is the closest center. Okay. Okay, so hopefully this is very intuitive. Sum of squared errors. We've been dealing with sum of squared errors since we started the class. There are versions of this that deal with things other than sum of the squared errors. The K-median clustering is just the sum of the errors. The K-center clustering is finding the maximum of all these distances. And the book talks about some algorithms that deal with those versions as well. So these fall within assignment-based clustering, which is, again, a subset of all the types of clustering. And the goal is then to find the set of the centers which minimize this, right? Find the set of centers. So our goal is to find centers C to minimize this cost function down here. Okay. Okay, it seems probably a little bit trickier. If though I will say, if we have exactly one center we're trying to find, if we only have one cluster, we have already solved this problem in this course very early on. If we want to find one center, we need to find a single point that represents all the data. And that is just the mean of all of the data. I can take the average of all the data. Okay, so, and we talked about that, and we actually motivated that from a Bayesian inference sort of perspective, where we said there was data was Gaussian noise from around one center, and we said if you assume that and found the maximum likelihood estimator, we are going to then the maximum likelihood estimator was going to be the single point was going to be modeled as the single point at the center at the average of all the data points. Okay, and actually for a version of this problem, the way to think about that is called the mixture of Gaussians, and we will talk about that on Thursday next week, which is motivated exactly the same way, and we can solve it for a mixture of Gaussians problem, and it's a kind of a motivated from this probabilistic point of view. But we'll mostly talk about this is the k-means version, and I will kind of state this at the in next week on Tuesday. Yeah.
So will this suffer from the same issue that linear regression did when you had a large number of powers, where you could just have a center for every
Yeah, right. So if I don't specify K, yeah, in this case, I'm given K. K is given as input to this version of the problem. Yeah, and we'll see as you get K larger and larger, you can make this cost function smaller and smaller. The same way with dimensional reduction, I can get zero error if I use the full d-dimensional space as my goal. So it's kind of suffers the same issue. If I want to minimize the error, including over what the size of the subspace or the number of clusters, if I make that arbitrarily big, I can get zero error. Yeah.
Yeah, I was also thinking, this doesn't mention this cluster. Is that just something you kind of?
Yeah, right. So this is often kind of simplified in that I'm kind of, it will implicitly do that. I'm only doing the first criteria. I want the inter-point distance to be small. And, by fixing K, I'm kind of implicitly the points across distances will kind of be large, but I'm not explicitly enforcing that. Yeah. Yeah. So this is kind of a much higher level view of clustering, and other views of clustering actually work on basically only look at this large thing, and they try and want to make sure that they keep points from different clusters far apart and ignoring the distance in between clusters, right? So there are other views of this that and some try and do both, and there's a whole landscape of these things. Yeah, great, good. So that's helping unwrap all the different variants that are hidden within inside this kind of very vague formulation. Okay. Okay, good. So this is a particular, the k-means formulation we'll talk about. And what I haven't explained, and what I want to spend the rest of the lecture doing, is to talk about this function here, this phi function, okay? And we're gonna talk about this to try and understand the kind of the geometry of this function. It's a well-studied kind of geometry problem, and I think understanding this will give a lot of intuition on how how the algorithm we'll talk about on Tuesday, Lloyd's algorithm, is going to work, and why this problem is challenging. Give you a glimpse into the curse of dimensionality that this gets very hard in high dimensions. And you see nice things happening in pictures in 2D because that's what I can draw, but I'll explain how this can kind of go haywire. Your intuition can go haywire in higher dimensions. Okay, so that will kind of be the focus of the rest of this lecture. Okay, and we're going to talk about Voronoi diagrams, and this is often called or at some point was called the post office problem. Probably now would be called like the nearest neighbor problem. All right, and so these are other problems which are well studied, and this will kind of give you an insight into some of the challenges in these. And again, the goal of clustering is, this is kind of implicitly in there, but the goal is to find the centers, okay? This is now the problem where we are, I'm going to say we are, given a set of k, centers or points, and I'll call these C, C1 up to CK, and these are going to be a subset of RD. Okay, so I'm going to be given these points. I'm going to draw a few more points than I had been drawing earlier to make this a little bit more, to show how this can be more interesting. Okay, so this will be C1, C2, C3, C4, C5, C6, and C7, okay? And I'm not drawing the data points here, right? The data points are kind of going to interact with this, but they're not going to be here. Maybe I'll draw C8 out here. Okay, And the goal is to understand this function, phi of c of x, which is the arg min of ci and c of the distance from x to ci, right? So I want to map everything to the closest point. And the way to do this is to think of decomposing the space into regions. Okay, so if I have a query point x, it maps to C2, right? If I were to move this slightly here, x prime, it still, I think, maps to C2, but at some point, it switches its allegiance over to C3. So think of these are kind of how the post offices are kind of put out. You want to go find your closest post office if you're a query, or this nearest neighbor search is kind of something that the data mining class talks a lot about, is given a set of objects. I have a query object. I want to find the most similar set in my database, right? And this is just a Euclidean version of it, but a lot of the methods map to Euclidean versions. And so this is a well-studied problem to do, but they typically do it approximately. We want to do this exactly. Okay, so I want to know, when do I switch allegiance from C2 to C3? And kind of typically what you would do is you try and draw these boundaries, right? So let's look between C1 and C2. Actually, don't think it. There's probably this boundary line where on one side it maps to C2 and the other side maps to C1. And I'm going to make the argument that this will always be these lines or line segments, which maps this boundary. It's the bisector between the 2 points. Okay, so if I take for instance, if I take the line between them and I take the midpoint, this green line should pass through this midpoint. Okay, but I can do this with a bunch of these points, and so and there's kind of this structure which is emerging here. See how well I can draw this. Okay, I have. Right, and you see one of the line I just drew here was the boundary between, when it switched the allegiance between C2 and C3, and x prime was closer to C2, but if I moved it a little bit, it's going to be switching to C3. And I kind of get these boundary structures. Each of these are indeed line segments, okay, and they meet at these vertices, okay. This is known as the Voronoi diagram, okay? And given a query point, if I know this Voronoi diagram, X, right? If I put kind of a query point in here, and I just look at it with my eyeballs, I can immediately say, well, this new point X is in the cell associated with C4, so it maps to C4. Right, so it really tells me I've decomposed the plane into these regions, which are telling me which point everything is mapping to. Right, so this is more complicated than the linear projection we were doing before for dimensional reduction. Right, it somehow is decomposing the plane in this way, and so in order to solve this, it seems like, well, I need to kind of I have to solve this diagram. I have to construct this diagram. Yeah.
And you just like have the point be the center of a circle that the radius is equal, like it touches to the center.
Yeah, right. So one way of thinking about this is that if I were to draw a circle around C1, right, and I'm drawing a circle around it, it's going to, there's another one around C2 of the same radius, right? So that these circles touch right at this boundary, right? But that's a different circle with a different radius than going to C4, right? So I can't just draw these circles and then know where it falls in. And there's some points kind of in near the corner here that have been left out as well, right? So this, just drawing the circles is not totally answering this question. Yeah. What's nice about this in, oh, is there another question?
Yeah, if a point lies like directly on like a big point with like exactly on a green line, is it like arbitrarily choose which section from them, or is it usually have a system for picking?
Yeah, so it depends on the application of when you're doing this. It could be arbitrary. You might always probably you might want it so it's well defined, and then I would typically say I'd assign it to the region with the lower index, right? So if it's on the boundary of C2 and C3, well, 2 is less than 3, so assign it to C2. That way it's consistent if you have a tie. Probably there are going to be some numerical precision issues at that point, and it's hard to know what's actually going to happen. You might not actually get a tie. One will always appear slightly less in most cases. But sometimes if like points are actually on a grid, then you actually do get well-defined ties on other grid points. And so that can happen. So it's good to keep that in mind. Yeah. Great. So, okay. What's nice about this is there are actually techniques from computational geometry that if I'm in the plane, right? Yeah, I'll just mention a few facts. The size of this, the size I can represent the whole Voronoi diagram in O of K space. This is in R2. Okay, I can do an O of K space. So it grows linearly with the number of sites I have. It's not growing kind of too bad. One region itself might have kind of O of K boundaries, but they can't all have O of K boundaries, right? I'll talk a little bit more about what this means later. In that I can actually, I can answer a query for X in O of log K time. Okay, so in logarithmic time, kind of like a binary search effectively, it's more complicated, but you have to decompose these and then do a couple binary searches, but it's O of log K time, you can retrieve which site is the closest. This is particular to R2. In R1, I can also do this. It might be illustrative just to think about the case in R1, right? So if I'm in R1, then I might have some sites, let's say, or center C1, C2, C3, let's say C4, right? Then the Voronoi diagram, right? It's this non-uniform decomposition, although it's the midpoints here. The midpoint, so, you know, again, the distance to the boundary of C3, the left boundary and the right boundary, is not the same. Okay? But then if I have a query X, I can tell which is the closest point, C3, and I can do this by basically building a kind of a balanced binary tree on top of these dividing points, and then on a query, I can kind of walk down and find the largest dividing point that is smaller than X, and then I know that that is going to be associated with C3, right? So if I can build a binary tree and I can walk down and log K, right? So in 1D, this kind of makes sense, but in 2D, this can kind of be done. In 3D, things get sort of complicated a little bit. Okay. So let me Yes, we've 5 minutes left. So let me just say some facts about it. Voronoi diagrams in RD. Okay, so in order to store the Voronoi diagram, I have to store the like all so all the boundaries, right? Remember, I had 2 points C2 and C3, and I need to store this boundary. Well, this becomes a D-1 dimensional kind of face. This is a subspace, right? And I have to store this in some way. I can store it with a normal direction, but I need to know when it ends, right? So if I have C1 here, right, then it ends when it intersects this vertex, right? This vertex where 3 of them meet is now going to be a D-2 dimensional face, or so facet, okay? And so in 3 dimensions, this object where 3 of these boundary faces meet is actually going to be a line segment, and then it has endpoints. Okay, in 4D, you have things of dimension 3, things of dimension 2, things of dimension 1, and points which are of dimension 0. And I have to store all of these in order to store this diagram. Okay, the cost of storing all of these in RD is going to have a space that is O of n to the D over 2, the C length of D over 2. Okay, so for D, so sorry, this is K, right? So think of a table here. So the space for 1 and 2, the space is going to be O of K, right? The space for 3 and 4, this is going to be K squared. This is asymptotic, right? Right, so it's all K squared space. If I get up to O of, like when the dimension is 5, this is K cubed, right? And so this grows with exponentially with the dimension, because I have to store all the different types of faces in order to just describe what the boundary is. If I want to look this up, if you have it, you can then access and kind of store these in kind of with some pointers to the different objects, and you can walk on these, and there's a whole bunch of methodology for doing these, but it gets complicated, right? I'm not going to want to store something this large that grows polynomially, K to the cubed. And its construction, people have worked on how to construct these efficiently. They come up in a lot of applications, and computer graphics, very similar things come up a lot. And people have worked at storing these, but they become quite complicated. And this is like going to be too large, too prohibitively large. Okay, so I want to query the nearest neighbor. So if I want to do nearest neighbor search, there's actually, right, so if I'm in D, and this is the time, right, then for dimensions 1 and 2, I can do log K. But if I'm in 3, well, it's no longer log K, but there's always something I can do for anything that is O of D. I can always just check all the distances. There are only K of them, right? So I can do this up to K, O of K time, right? So I can always just check. For these, I just check all. So all the distance, I just measure all the distances to all of the objects, and I see which one is the smallest. Okay, so I can do that, and this is how the algorithms will run. They will compute the distance to all the objects, and they'll take the one that's the smallest. But it means that I can't like really know the structure, and I can't like do the same sort of detailed analysis I could, and the same simple tricks we use for like dimensional reduction and other problems. I have to kind of, as we'll see, we'll come up with an algorithm that is going to work in an iterative process. And the iterative process will sometimes give you the right answer, and sometimes it won't. Okay, there are algorithms that study these Voronoi diagrams and come up with the exact right answer and say, how fast can I do that? And this has been studied, and it's often exponential time in the dimension to do it. Okay, to do it exactly. So that's why we're going to default to this other algorithm, which is not going to have as strong guarantees. And so we'll talk about it. I'll give you some hints on how to make it work quite successfully very often in practice. Okay, great. So we'll stop there and have time for the quiz. We'll talk more about kind of more solutions and algorithms than these challenges in the next lecture next week.